Hi, my name is Hyun-Soo Yang from Seoul National University. The title of my research is Distributed Rotor-based Vibration Suppression for Flexible Objects Transport and Manipulation. In industry, carrying or manipulating a large and heavy object is a common task. These large objects handled by multiple workers or large crane. Also, there have been many attempts to partially or fully handled by robotic systems, typically in the assembly line in manufacturing. In recent years, there are several attempts to bring the robotic system to outside the factory. However, large-sized objects have to be handled in case central mass is far from the end effector, so the size of the object is limited or grasping point should be close to central mass or the robot should be large enough. To relax this limitation, one possible direction is cooperation of multiple robots. Cooperation of multiple ground manipulators can provide high payloads, however, the permitted torque is relatively low. In addition, the workspace of object is limited by the workspace of ground manipulator. On the other hand, the aerial robots have unlimited workspace, but the pairs of aerial robots is relatively low than ground manipulator. From this background, we propose a heterogeneous robotic system cooperating ground manipulator and aerial robot called magmas. We utilize these heterogeneous robots in a complementary manner. However, we found that the vibration for long bar or pipe is crucial. In addition, the conventional multi-rotor drone is optimized for flight but not for manipulation. To solve this problem, in this research, we propose distributed rotor-based vibration suppression module. The contribution is following. First, we propose a design optimization framework to optimally design a module for manipulation. Second, we propose a controllability analysis. And last, we also propose an optimal placement for the multiple modules on the flexible load. And relevant to us, there were researches about flexible link manipulator. For this problem, there is a mismatch between the number of actuation and degree of freedom. So this is underactuated problem for vibration. Since the actuator is located on the joint, so the system is non-collocated. There is a non-minimum phase dynamics issue and the results are limited to small scale. There were results on large-size manipulator with rotor actuation or tendon, but these results are limited to lightweight system for vision inspection or only for rigid links. This is overview of presentation contents. First, I will explain about how we designed the RVM. In general, multi-rotor drone is equipped with core-linear rotors for its simple structure and hovering efficiency. The drone should have additional mechanical parts to connect to flexible load while allowing free rotation. In addition, the minimum number of required rotors is 4 to maintain the hovering state. On the other hand, the RVM is designed for vibration suppression of flexible load. Therefore, the rotors does not need to be co-linearly aligned. Also, we designed the module to be easily attached to and detached from the flexible load. Since the RVM does not need to have flying capability, the required number of rotors is less than 4. From this idea, the objective of design is maximizing the feasible thrust generation capability in the sagittal plane while minimizing undesirable range. To minimize the size and weight of each module, we utilize 2 rotors, which is the minimum number of rotors. This design optimization can be formulated as the following constraint optimization problem. The cost function represents the feasible thrust area maximization in sagittal plane. The first constraint means unit vector constraint for rotor direction. The second constraint is module size limit. The third and fourth constraint means actuator-induced and gravity-induced torsional torque balance. And the last constraints represent minimization of airflow interference between 2 rotors by preventing overlap between airflow cylinders. The resultant optimized module design is shown in the figure. Then I will explain about system modeling. This modeling includes vibration of flexible load and control design framework with controllability analysis. The system configuration can be defined by joint angle for manipulator and position of flexible load. The position of flexible load includes diffraction term W. Here we assume that the RVM is rigidly attached to flexible load, so the position of RVM is expressed by position along the flexible load. The governing equation of this diffraction is Euler-Bernoulli beam equation. This partial diffraction equation can be solved by separation of variable methods, so the solution is expressed by mode shape phi and time-varying variable delta. In theory, there are infinite number of vibration modes. However, in practice, here we assume n number of vibration modes. The kinematics of the system can be derived by differentiating each configuration, and then we can get all the Lagrange robot dynamics from kinetic and potential energy. The robotic system dynamics consists of manipulator and flexible dynamics and its coupling between 2 systems. You can see that the manipulator cannot directly control the flexible load dynamics through control mapping matrix BQ. Also, we assume n number of vibration modes, but the number of RVM can be arbitrary number, so there might be a controllability issue. The important thing is that the inertia matrix m delta and stiffness matrix k are constant diagonal metrics. Based on the dynamic structure, we can design following control framework for each subsystem. The manipulator holds overweight of flexible load and tracks relatively slow nominal trajectory of flexible load. This nominal trajectory can be calculated by assuming there is no deflection. Since the ground manipulator is fully actuated, the tracking control is straightforward. Next, the distributed RVMs on the flexible load should suppress relatively fast vibration, and it also needs to compensate deflection induced by gravity. The problem is that depending on the number of vibration modes and RVMs, the system can be underactuated. So next, we provide controllability analysis. From the dynamic structure of a whole system, the inertia and the stiffness of flexible dynamics is constant. So the flexible load dynamics can be treated as a linear system by assuming the rest of term as disturbance. The state space form is given in the second box, and this system is linearized along the trajectory of zero deflection at the load tip. This trajectory represents gravity compensation. Given linearized flexible load dynamics is controllable if this controllability matrix have full load length. Here, the controllability matrix consists of some matrix CS, and the full load length condition is equivalent to each matrix. And we check the determinant condition of matrix multiplication, which is equivalent to full load length condition. The properties of some matrix CS is summarized in lemma 1. The second property says that if the first term on the right-hand side is larger than 0, then the determinant is always larger than 0. This property leads to the sufficient condition of controllability. This theorem explains controllability condition. To satisfy this inequality, we can come up with following three conditions. First condition is placing condition. To meet this condition, at least one RVM should be attached not on its node, since there is zero amplitude at the node position. Second condition is tilting condition. To preserve this condition, RVM should be able to produce vertical force, which can be always guaranteed by RVM design. And the last condition is mode independence condition. This condition is always guaranteed, because different vibration modes always have distinct frequencies. Next, I'm going to explain how to optimally place multiple RVMs. The controllability analysis explains where not to place the RVMs to preserve controllability. However, it does not explain where we need to place the RVMs and what is the optimal placement. For this, we need to quantify control capability of given RVM placements. The controllability gramian characterizes the minimal energy required to steer a state from 0 to a certain state, so here we adopt controllability gramian to evaluate the control capability of given RVM distribution. With the small damping assumption, the controllability gramian can be approximated as a diagonal matrix, and its diagonal components are calculated by natural frequency and the summation of mode shape at the RVM location. Natural frequency is determined by material of flexible load, and then the optimal placement is determined by the beta term, which is the summation of mode shape of given RVM placement. Physically, this controllability gramian matrix structure explains that the optimal placements of RVM is led to maximizing the amplitudes of mode shape at the RVM location. This is experimental result. Here we exert external disturbances to the flexible loads every 3 to 5 seconds. You can see that the vibration stays for a long time without RVMs. On the other hand, with RVMs, the vibration is suppressed right after the user exerts the disturbance. In next experiments, the external disturbances are replaced by motion-induced vibration. This experiment also shows that the RVM effectively suppresses the vibration, while the vibration is not suppressed without RVMs. In next two experiments, we add an additional motion to orientation to show the effect of reducing required torque for manipulator. Without RVMs, the deflection is too large, so the trajectory is shifted. On the other hand, with RVMs, it can maintain its desired motion. In this experiment, we add external disturbance to the previous experiment, so the required torque for the manipulator is even larger than the previous experiment. Without RVMs, again, the required torque exceeds its torque limit. On the other hand, with RVMs, the manipulator works within the torque limit. This is conclusion of research, and possible future work includes realization of actuation, battery, and sensing integrated onboard module, and interaction or cooperation with human. Thank you for listening, and I hope to see you at paper discussion.